And this is steady state mass transfer. So we think a reaction diffusion system, such as fermentation, nucleation, catalyst, battery electrode, baking, coffee roasting, etc. We usually use a mass transfer coefficient, which is really an engineering approximation for a mass transfer process. So assuming we have these two phases, and we have this boundary or interface between the phases, and we assume that all changes occur within this like boundary of the interfaces or close to. And this assumption is necessary for mass transfer coefficient to work, which may or may not be accurate. So rate of mass transfer between two phases are correlated with a concentration differences between the phases and times the interface area, which makes sense as the concentration difference is a driver of the mass transfer according to Fick's first law, although we know that in actuality the real driver it is the chemical potential differences, but it's close enough. And the larger this area, the more faster the rate of mass transfer, so multiply by that. So we have this system. If you think of the catalyst system, where there's a catalyst surface and then there's a liquid phase on top of it, where there's a bulk regime, and then there's a little boundary layer, where in this z-axis we have this 0 here, and then the thickness of the boundary layers corresponds to delta. And this interface layer, or this where the boundary layer starts, we can assume the concentration will be same as the bulk concentration, and then they go down to the surface, and it gets immediately transitioned into a B, or compound B, and this B gets sent back up. So there will be some flux of A going down, and then some flux of B going up. And for this system, the equation would be the flux N of A, compound A, which is a unit of mole concentration of, or mole of A over meter squared times second, which is really representing in this specified area how much mole of A are moving at certain times, which is the flux. And that is the K, the coefficient, mass transfer coefficient, so K prime C, which can take account for all the areas and other stuff that relates to the mass transfer rate, times the concentration difference, which is the concentration at bulk minus concentration of A at this surface of catalyst. And in this case, the unit of this K would be meter per second, and this concentration will be this. Besides, for a different system, we have a similar equation where Kx, where xa 0 minus xa delta, and 0 and infinity are pretty much same because of this assumption we have made over here. So this is for a liquid system, y is for gas system, and these are for the mole fraction. And for gas system, sometimes we use the pressure instead. In this case, because they have all different units, which is this is concentration, this is mole fraction, they will all have different units of K to satisfy the flux, which all have same unit. So in this kind of example question system where there's a catalytic surface, and then there's a bulk regime, and there's some reaction happening on the surface, we can kind of interpret it in two ways. Or there are two different reactions, I guess. One is homogeneous and one is heterogeneous surface reaction. So homogeneous reaction, example, there's the R dot, which represent this is a rate. So reaction rate of a, and with the superscript V represent the volume. So we are looking at the volumetric reaction rate of compound A. And we have this plus minus sign because it can either, the catalyst may either generate or consume the compound A. And we have this kVA, which doesn't have prime. And this is the reaction rate constant and times concentration of A. For a heterogeneous surface reaction, which denotes that it is only happening on the surface rather than entire volume, it is R dot SA, which represent S means the surface area, plus minus, either generating or consuming, a reaction rate constant KSA times CSA. In this case, the unit of the concentration is mole over centimeter squared. And we can further analyze it because there are two different domains on the catalytic surface and then on the bulk regime. We need to add a partition coefficient. It's the compound's affinity towards one phase or another, to make it a truly more realistic equation. And this here C represent a bulk concentration in equilibrium with the surface. So this looks kind of makes sense, but now the unit doesn't work out because we added partition coefficient. So to make this unit work again, we have to add a volume over area to make it into rate again. And sometimes we just combine all this partition coefficient, volume over area, which is for just unit adjusting, and then just Ka, and just call it just Ka. But so if you look at a reaction within a porous media, in the small scale, we can kind of try to determine the surface area of each pores and try to calculate it, and then calculate the porosity, and you sum those all area up. Then in that case we would use a heterogeneous surface reaction. But if you're more interested in a bigger scale of interpretation and a little bit easier way, where we're not super interested in about very tiny little precisions, and the homogeneous reaction would work just as well, where we're interpreting as, instead of each surfaces of these little pores, we're considering the entire volume of porous media. We're looking at the entire volume instead of just each little tiny surfaces. In that case, we can make the effective homogeneous reaction equation where R dot A V, so which denoting volume, and effective. We have there's KSA, same as here, and then volume over area for the unit conversion, and then concentration of A at the surface. So now we are changing this area equation, the surface area, to a volume. And now formulating governing equation. For shell balance equation, which is an approach of taking a tiny little piece, and then you calculate it for that piece, and then you make that piece infinitesimally small to rather accurately evaluate the entire system. First, we have to assume that the reaction occurs within shell are source and sink for reacting compound. The reaction at boundary or volume are not a source and sink of the compound. And within shell, you start with the light-footed expression of this, where flux equal to XA total flux minus concentration, diffusivity, and this. And these are some for conditions that represent the reaction or relationship of A and B, where MB is equal to 0, and the NA equal to negative MB, which kind of like goes hand in hand. Like if A turns into B, then the flux would be like opposite, which makes sense. At the surface, in the surface area, the half of A is equal to B, so hence that the flux of A is equal to half the flux of B, and the A is infinitely dilute, basically. Boundary conditions. We have to assume constant concentration. You have to solve these, just like Navier-Stokes equations, where we have a lot of assumptions to kind of like cancel out some components. We have to assume that at the surface there's a constant concentration, and flux is also constant at surface, and the flux of A is equal to this equation, Kc times the concentration difference. The chemical reaction at the surface is following this equation. Flux Na delta over here at flux here is equal to K times concentration. And that system is represented over here, where 2A molecules are turning into B, 1B molecule, and this is happening instantly and irreversible. And we're trying to figure out the flux of A and concentration profile of A at this boundary layer. Condition will be that boundary condition will be that at Z is equal to 0, the interface between bulk and boundary layer, the XA is equal to XA0, which is kind of intuitive, and at the interface, the concentration equal to A equal to delta. So what we're representing here with the shell balance, we have this like tiny piece that we took off of here, kind of shows like that. Our flux is going here, NAZ, Z direction, and it's coming out as Na at Z plus delta Z, which is the thickness of the shell, which we're going to make it into like approach 0, and then we have this width and this like side length. So mass balance equation would look like in and out of this flux, in minus out plus generation minus consumption is equal to accumulation of A. But they all goes to 0, at least accumulation. So there's no generation of consumption because this is not at the surface of this catalyst. Accumulation goes to 0 because this is steady state, which means that if accumulation was non-zero, then at every time there's going to be a little accumulation, and then if we do it for infinitely long time, then the concentration of A at this point is going to be ridiculously high, which doesn't make sense. So at steady state, accumulation is equal to 0. And so what we have left is the in minus out is equal to 0 for mass balance.